Greetings. The year 1944 marked a turning point in aerial warfare, when the Allies, armed with revolutionary technology and unmatched industrial capacity, began to dominate the skies over Germany. At Recklinlatz airfield, German engineers scrutinized a single captured American P-51 Mustang, shot down during the first escort mission to Berlin. Yet what they discovered challenged everything they thought they knew about American airpower. How did this fighter achieve a range that defied previous assumptions? Could a simple paper cylinder hold enough fuel to keep it airborne for nearly 6 hours? And what did this reveal about American manufacturing ingenuity? Was it merely an aircraft or a symbol of industrial resilience? These questions converge into one. How did the Allies, through resourcefulness and mass production, turn a small fighter into an unstoppable force deep into German territory? I promise, in this video, we'll trace every detail, separating fact from fiction, and reveal how a seemingly simple object, made of glued craft paper, reshaped the entire war. The story begins now, with the first chapter, uncovering the secrets behind the legendary P-51 Mustang and its extraordinary range. March of the year 1944 found the scene set at Recklinlatz airfield, situated in the heart of Mecklenburg, Germany. By this time, the meticulous examination and analysis of captured enemy aircraft had become an indispensable and highly prioritized task for the Luftwaffe's Technical Intelligence Division. At the renowned Air Testing and Evaluation Center in Rechlin, often referred to as Air Probungsstelle, teams of dedicated engineers, seasoned pilots, and technical analysts worked tirelessly to uncover every possible advantage that the Allies might wield in their relentless aerial campaign. The discoveries made during the early months of spring in 1944 would prove to be revolutionary, fundamentally reshaping the German understanding of American industrial prowess and redefining the prospects of the aerial conflict over the Third Reich. Among these revelations came the arrival of a single, heavily scrutinized aircraft, the American P-51 Mustang, that had been brought to Rechlin for detailed examination. This particular Mustang, the first of its kind to be captured in the ongoing air war, was transported by rail on the 6th of March that year from a crash site near Brandenburg. The aircraft had been shot down 2 days earlier during what marked the first American fighter escort mission to Berlin. The pilot had perished upon impact, his life lost amid the wreckage, but remarkably, the aircraft itself remained largely intact, providing the German technical teams with their most complete and promising example of the aircraft to date. This was especially significant because the P-51 Mustang represented a new generation of fighters, capable of challenging previous assumptions about the capabilities of American airpower. Leading the initial examination was Man V.A. Bombach, a seasoned engineer specializing in aircraft development, who would later go on to command the renowned Kampfgeschwaden. His team carefully studied the aircraft's construction and design, but perhaps most revealing were the navigation charts still stored in the cockpit. Charts that detailed the route from an airfield called Debden in England directly to Berlin and back, covering a round trip of over 1,000 miles. The process of technical evaluation began immediately after the aircraft's arrival. Prior intelligence reports had suggested an increase in American fighter activity well beyond German borders, yet official assessments had maintained that single-engine fighters lacked the range necessary for extended escort missions deep into German territory. The prevailing belief was rooted in the analysis of earlier captured aircraft such as the P-47 Thunderbolt and the P-38 Lightning, both of which had demonstrated limited operational reach into German airspace before fuel limitations compelled them to turn back. However, the events of March 4 and 6 of 1944 shattered these long-standing assumptions. On March 4, newly transitioned P-51 Mustangs from the 4th Fighter Group, flying their initial missions in the aircraft after switching from P-47s just days earlier, had successfully escorted a small formation of bombers toward Berlin. Despite adverse weather conditions and communication difficulties, only 32 of the bombers managed to reach the target, but the significance of this mission was unmistakable. American single-engine fighters had achieved the milestone of reaching Berlin, engaging in combat, and returning safely to England. Just 2 days later, on March 6, a formidable force of approximately 660 bombers launched a daylight attack against Berlin, accompanied by an escort of over 150 P-51 Mustangs, along with groups of P-38 Lightnings and P-47 Thunderbolts. These escort fighters engaged Luftwaffe interceptors over the German capital, fiercely defending the bombers and guiding them safely back home. This event signified not a fleeting anomaly, but a strategic breakthrough. The Americans had effectively solved the escort fighter problem that had long plagued their air campaigns. The implications of these developments were profound. For the first time, the Germans recognized that their previous limitations and operational assumptions about American fighter range and capability were no longer valid. The victorious missions of March had demonstrated that the Allies could project air power deep into the heart of Germany, challenging the very notion that German defenses could contain or defeat such an advanced and long-range fighter force. The Luftwaffe's analysts and commanders now faced a new, more formidable aerial threat, one that would fundamentally shape the future of the air war over Europe. Colonel de Jagdflieger, one of Germany's most accomplished fighter aces with a record exceeding 100 aerial victories, had continued to fly combat missions during this period despite his official administrative duties. His encounters with formations of American P-51 Mustangs over Germany were swift and unmistakable, and he recognized their significance immediately. These encounters prompted him to scrutinize the capabilities of these fighters beyond what standard intelligence reports suggested. In his detailed combat evaluations, submitted through official military channels, de Jagdflieger observed that American fighters operated at full combat readiness over Berlin. They engaged with fierce determination, displaying no signs of fuel conservation as they pursued their targets. Instead of flying near their maximum range, these fighters seemed to have ample reserves, a fact that sharply contrasted with the prevailing assumptions held by Luftwaffe intelligence, which believed the P-51s had a limited operational radius. Gallen reports from the front lines reinforced this discrepancy, highlighting the P-51's exceptional ability to perform at high altitudes, above 20,000 feet, where it outstripped both the Messerschmitt Bf 109 and the Focke-Wulf Fw 190 in terms of speed and agility. These high-altitude advantages made the Mustang a formidable opponent, capable of quick interceptions and evasive maneuvers that German fighters found difficult to counter. At the Reiklan Aircraft Testing Facility, a meticulous technical examination focused initially on understanding how the American fighters achieved such impressive range. A team of engineers took precise measurements of the P-51B's internal fuel capacity. The aircraft was equipped with 2 wing tanks, each capable of holding 92 gallons of aviation fuel, totaling 184 gallons in the wings alone. Additionally, a fuselage tank, with an 85-gallon capacity, had been added during later production runs to extend operational range. This fuselage tank had been a significant recent modification, integrated into the P-51B design to allow for longer missions. When combined with the wing tanks, the total internal fuel capacity was approximately 269 gallons. The engine powering the aircraft was a Packard-built Merlin, a licensed version of the Rolls-Royce Merlin, a revolutionary power plant that transformed the Mustang into a high-altitude performer. The Merlin's fuel consumption varied depending on the power settings used during flight. At economical cruising power, the engine burned roughly 60 gallons of fuel per hour. Under more typical cruising conditions, fuel consumption increased to about 75 gallons per hour. German engineers used these figures to perform detailed range calculations, aiming to determine the true operational limits of the P-51B. Based on the internal fuel capacity of about 269 gallons and an average consumption rate near 70 gallons per hour at cruise settings, they estimated that the Mustang could stay airborne for approximately 3 hours and 58 minutes. At its cruising speed, roughly 300 miles per hour, this translated into a maximum theoretical range of approximately 1,140 miles. Such a range was just enough for a round-trip mission from English bases to Berlin, barely, with no reserves for combat or unforeseen circumstances. However, actual combat reports painted a different picture. American fighters engaged in extended dogfights over Berlin, sometimes lasting 15 to 20 minutes before disengaging and returning home. During these high-intensity encounters, fuel consumption surged beyond 100 gallons per hour, especially when fighters operated at full power and engaged in combat maneuvers. Under such conditions, the aircraft should have been incapable of returning to base without refueling or risking ditching. This apparent contradiction between calculations and observed combat behavior raised a critical question. How did these fighters sustain such prolonged engagements and return safely? The answer became clearer upon closer inspection of the aircraft's wing structure. German technical specialists discovered the presence of standardized hard points beneath each wing, designed for external stores. These attachment points included fuel line connectors, indicating they were meant to accommodate external fuel tanks, drop tanks, used to extend the aircraft's operational range. Drop tanks were not a new technology. German fighters had utilized external fuel tanks since the Battle of Britain. Their purpose was to augment the aircraft's range significantly, allowing fighters to undertake longer missions without sacrificing performance or risking fuel exhaustion. The realization that the P-51 in combat was often carrying additional external tanks explained how it managed to sustain prolonged dogfights over Berlin and still return safely, despite the high fuel consumption rates observed during combat. In conclusion, the German engineers' findings clarified the mystery surrounding the American fighters' endurance. The P-51 Mustangs, with their ability to carry external fuel tanks, could extend their operational range well beyond the limits suggested by internal fuel capacity alone. This technological advantage, combined with the fighters' high-altitude performance and fuel reserves in external tanks, allowed them to undertake long-range missions deep into enemy territory, engaging in sustained combat operations that previously seemed impossible based on internal fuel calculations alone. The history of aerial warfare is rich with innovations, and one significant advancement during the Second World War was the development and deployment of external fuel tanks, commonly known as drop tanks. These tanks played a crucial role in extending the operational range of combat aircraft, allowing them to undertake missions that would otherwise have been impossible within their standard fuel capacities. For instance, the legendary Messerschmitt Bf 109, a mainstay of the German Luftwaffe, was capable of carrying a drop tank with a volume of approximately 300 liters. This additional fuel supply was particularly valuable during long-range escort missions or deep penetration strikes. Similarly, the Focke-Wulf FW-190 extensively utilized drop tanks for missions requiring extended endurance. The primary advantage of these external fuel tanks was the ability to augment an aircraft's fuel load without increasing its internal weight, thus preserving maneuverability and speed during combat. The typical procedure was to attach these tanks before takeoff, providing extra range, and then jettison them once the aircraft approached the combat zone. Removing the empty tanks before engaging the enemy helped reduce drag and weight, thereby improving the aircraft's agility and speed in critical moments. This practice became standard across many air forces, serving as an essential tactic for extending mission endurance. While it was well known that the Americans employed drop tanks, the key questions for the Germans centered around the tank's capacity, how large they were and, perhaps more critically, how the United States produced such tanks in sufficient numbers to sustain their relentless operational tempo. This curiosity sparked an immediate and intensive effort to locate and analyze American drop tanks from the recent missions in March. Intelligence units meticulously mapped potential jettison points based on the locations of aerial engagements reported by Luftwaffe pilots. They understood that pilots typically released their external stores, like drop tanks, upon encountering enemy fighters, as these external loads could hamper maneuverability and reduce speed. Consequently, search parties, comprising Wehrmacht personnel and Hitler Youth volunteers, spread across the countryside northeast of Berlin, systematically scouring fields and forests for debris from these air battles. Within just 3 days, the effort bore fruit. Several objects, likely remnants of dropped tanks, were recovered from the terrain in the region. Most of these pieces were fragmentary, damaged or crushed by impact or the fall itself, making detailed analysis difficult. However, there were 2 notable exceptions: relatively intact tanks that had landed softly in soft soil or winter wheat, cushioning their fall and preserving their structure. These recovered tanks proved to be a game-changer for German understanding of American industrial manufacturing. Their design and construction revealed unexpected sophistication. The tanks were cylindrical, measuring approximately 108 inches in length and about 22 inches in diameter at their widest point. Volume calculations indicated that each tank could hold roughly 108 US gallons, or around 400 liters of fuel. Having identified the capacity, the Germans realized that 2 of these tanks could supply an additional 216 gallons of fuel, effectively increasing the total internal fuel capacity of a P-51 Mustang to about 485 gallons. This augmented fuel load enabled the aircraft to stay aloft for approximately 6.7 hours at cruising power settings, translating into a range that exceeded 2,000 miles, more than enough for missions such as the bombing run over Berlin, with plenty of reserve fuel for unforeseen contingencies. The mathematical implications of this increased fuel capacity became immediately clear. However, what truly captured the attention of German engineers and analysts was not just the tank's volume but their remarkable construction. On careful inspection, it became evident that these tanks were not fabricated from metal, as might be expected, but from a different, more innovative material. Running a hand along the surface of the tank revealed a texture unlike any metal, no smoothness associated with aluminum or steel. The exterior was coated with a shiny silver paint, but this superficial layer was deceptive. When engineers delicately scraped away a small section of the paint near the tail cone, they uncovered the true nature of the tank's material beneath. It consisted of multiple layers of heavy paper, each layer perhaps half a millimeter thick, that had been compressed and laminated into a durable, functional structure with an adhesive binder. This construction was neither accidental nor primitive, it was a carefully engineered design. The nose and tail cones of the tank were formed from overlapping strips of this layered paper, pressed into shape similar to the traditional papier-mâché technique. These overlapping pieces created a distinctive scalloped pattern along the tank's surface, a visual signature of the manufacturing process. The central section, however, was seamless, wrapped in continuous layers around a cylindrical form, providing strength and integrity. The fuel fittings attached to the tanks were made of brass, precisely machined and carefully sealed, indicating a high level of manufacturing sophistication. Peering through the inspection, engineers could see that the entire assembly was purposefully designed, combining innovative material science with traditional engineering principles to produce a lightweight, yet durable, external fuel container. This discovery of an unconventional construction material, layered paper, shocked German analysts, as it defied the filler's cap revealed an interior surface coated with a substance that appeared to be a lacquer based on cellulose, specifically designed to withstand the corrosive effects of aviation gasoline. This detail suggested a deliberate choice of materials aimed at durability and chemical resistance, key factors for military fuel storage. To better understand the construction of these innovative tanks, experts specializing in German materials science were brought in. Their meticulous analysis uncovered that the lining was composed of kraft paper, manufactured through a chemical pulping process that produced exceptionally strong and resilient cellulose fibers. This type of paper was not ordinary. It was the same high-strength material used in the manufacture of heavy-duty shipping containers and industrial-grade packaging, known for its ability to withstand significant stress in harsh environments. The adhesive used to bond the paper layers was identified as a form of resorcinol formaldehyde resin, a thermosetting polymer renowned for creating bonds that are stronger than the paper itself once cured with heat. The lamination process involved at least 12 separate layers of this specialized paper, each carefully oriented to optimize strength in multiple directions, providing structural integrity comparable to, if not exceeding, that of conventional metal tanks. Inside these tanks, wooden baffles were installed, designed to prevent fuel sloshing and surging during rapid maneuvers. These anti-slush baffles played a crucial role in maintaining stability and consistent fuel flow, especially during intense flight operations. The entire construction process appeared to be highly standardized, indicative of a mass production approach that aimed to produce large quantities efficiently and uniformly. Despite their unconventional materials, the overall weight of an empty paper tank was around 80 pounds, which, while slightly heavier than a smaller metal equivalent weighing between 65 and 75 pounds, did not significantly compromise payload or performance. The use of paper did not necessarily mean a lighter tank, but it offered other compelling advantages, particularly in terms of production speed and resource availability. This realization immediately caught the attention of the technical staff at WWII. It became clear that the Americans were manufacturing fuel tanks from materials that were not classified as strategic resources. Paper and wood-based resins did not depend on the metals, such as aluminum and steel, that had become increasingly scarce in wartime economies. This approach represented a strategic advantage, as it reduced reliance on critical metal supplies. Moreover, the manufacturing process itself did not require specialized equipment for metalworking, nor did it need skilled metalworkers, welding, or sheet metal forming, complex and resource-intensive steps typical of traditional tank production. Instead, these paper tanks could be produced in any paper mill or industrial packaging facility with only minor modifications to existing machinery. Given that the United States had hundreds of such facilities across the country, the potential scale of production was staggering. If even a modest percentage of American paper production capacity was diverted toward manufacturing these drop tanks, the output could easily reach tens of thousands of units each month. The tanks showed no serial numbers, no manufacturer markings, or any indication of limited production runs. They were essentially mass-produced commodities, designed to be expendable after a single use. This led intelligence analysts to examine the capacity of the American paper industry more closely. Prior to the war, the U.S. produced around 12 million tons of paper annually, with output increasing significantly during wartime mobilization efforts. Even if only 1% of this capacity was allocated to producing drop tanks, it would result in the manufacture of over 100,000 tanks every month, far beyond what would be necessary for operations involving the P-51 fighters or similar aircraft. The limiting factor was not the availability of raw materials but rather the manufacturing capacity, specifically, the equipment and labor needed to assemble these tanks. Fortunately, this type of production could be performed by semi-skilled workers after minimal training, making it highly adaptable and quick to scale up. These paper tanks exemplified industrial efficiency and resource optimization on a grand scale, a feat that German planners found difficult to comprehend fully. Further detailed analysis revealed additional insights. These tanks were strictly designed for single use, emphasizing their role as expendable, mass-produced items rather than durable, reusable components. This strategic shift in manufacturing reflected a focus on quantity, rapid deployment, and resourcefulness, transforming the landscape of wartime logistics and resource management. During the course of the war, one of the most intriguing innovations in aerial logistics was the development and deployment of specialized fuel tanks, which significantly streamlined the operational capabilities of fighter aircraft. These tanks were made from a lightweight material known as resourceful impregnated paper, which was ingeniously designed to form a durable yet disposable fuel container. When initially created, the adhesive used in their construction was remarkably effective at bonding the paper components together, forming a sturdy seal that could withstand the rigors of flight. However, this adhesive revealed a notable limitation. Over time, with continuous exposure to aviation gasoline, the bond gradually weakened. Prolonged contact with the fuel slowly dissolved the adhesive, compromising the tank's structural integrity if left unused for extended periods. Intelligence reports, combined with interrogations of captured American aircrew, shed light on the operational procedures surrounding these paper tanks. It emerged that the tanks had to be filled immediately before a flight. Once filled, they could not be stored for more than a few hours without risking leaks or failure. Fortunately, this constraint did not hinder operational efficiency, as fighters underwent their fueling process as a routine part of pre-flight checks. The tanks were intended for use during a single mission, after which they would be jettisoned once their fuel was depleted. This one-time use design was not only practical but also simplified logistics dramatically. There was no necessity for retrieving, cleaning, inspecting, or repairing the tanks, which significantly reduced maintenance efforts and resource expenditure. The design also included color coding, a feature that proved highly beneficial during ground operations. Paper drop tanks were painted in a distinctive silver hue, contrasting with the gray color used on metal tanks employed by American forces. This visual distinction allowed ground crews to quickly identify the type of tank during fueling processes, enhancing operational speed and reducing errors. The silver coating on the paper tanks served a further purpose. It reflected solar heat effectively, thereby lowering the internal temperature of the fuel and reducing evaporation losses as the aircraft circled at high altitudes. This detail underscored the thoughtful engineering considerations embedded in the tank's overall design. Every element of these tanks reflected meticulous engineering aimed at optimizing mass production and field deployment. By the end of March in the year 1944, German intelligence had traced the origins of the paper drop tanks back to British development efforts. The British Air Ministry had initiated the development of impregnated paper fuel tanks during the year 1943, primarily as a strategic measure to conserve vital metals, especially aluminum, which was in limited supply during wartime. The Bowater-Scott Corporation, with its expertise in paper manufacturing, was tasked with developing a feasible production process, transforming the concept into a practical, scalable product. These innovative tanks entered service with Royal Air Force fighter squadrons by late 1943, quickly demonstrating their utility in combat scenarios. American forces, recognizing the advantages of this design, rapidly adopted the concept, engaging multiple manufacturers across both Britain and the United States to produce these tanks for use by United States Army Air Force's fighter groups. Although the initial impetus for this resourceful solution stemmed from British resource shortages, the sheer manufacturing capacity of American industry allowed for mass production on an unprecedented scale. This technological advancement had implications that extended well beyond simple fuel storage, highlighting broader trends in wartime industrial innovation. As the Germans studied captured American equipment, their technical staff embarked on a comprehensive review, searching for other examples of industrial ingenuity and mass production techniques. Their findings painted a clear picture. While American hardware was not always superior in the performance of individual components, German optics often outperformed their American counterparts, and German small arms were frequently more complex and refined. The overarching characteristics of American manufacturing were consistently superior. American equipment was more reliable, more standardized, and produced on a much larger scale, ensuring availability in quantities that the Germans could scarcely match. The American approach prioritized ease of mass production over perfection in individual parts. Components were designed from the outset to be produced efficiently by semi-skilled workers, utilizing standardized tooling and processes. Parts were made interchangeable between units, eliminating the need for hand-fitting during assembly, which further accelerated production times. Assembly line techniques, perfected in American industry, reduced manufacturing costs, increased output, and ensured rapid deployment of vital equipment. This stark contrast with German production methods, which often emphasized craftsmanship and meticulous individual assembly, underscored the broader strategic advantage American industrial capacity conferred during the war. Hodge was a man of exceptional standards, and the German approach to manufacturing reflected this dedication to precision and craftsmanship. German weapons and military equipment, in particular, were often considered engineering marvels, meticulously hand-fitted by highly skilled artisans whose expertise ensured each component met exacting standards. A German tank engine or aircraft power plant exemplified the zenith of precision engineering, embodying a level of craftsmanship that set them apart. However, such perfection came with significant trade-offs. Building these advanced pieces of machinery demanded highly specialized labor, sophisticated tools, and extensive time for each unit to be crafted. As a result, the rate at which these finely produced items could be manufactured was inherently limited, constrained by the availability of master craftsmen and the intricate, precision machinery required for their production. In contrast, the Germans excelled at producing superior individual items, each one a technical masterpiece in its own right. Yet, the Americans prioritized mass production, generating sufficient quantities of equipment that, in the realm of industrial warfare, often proved more decisive than perfection alone. Their strategy focused on producing large numbers of adequately effective items, ensuring that overwhelming volume could compensate for, or even surpass, the quality of individual German pieces. A compelling example illustrating this principle is the production of the P-51 Mustang fighter aircraft. The North American Aviation Company initiated the design of the Mustang in response to a specific British military requirement in the year 1940. Remarkably, the prototype, designated NA-73X, was completed within a mere 117 days after the initial contract was signed, an extraordinarily rapid development cycle by aviation standards. The first flight of this prototype took place on October 26, 1940, marking the beginning of what would become a legendary aircraft. By the year 1944, North American Aviation was producing P-51 variants at two major facilities spread across the United States. The plant in Englewood, California, reached an average output of around 364 Mustangs per month during its peak production periods. Meanwhile, the plant in Dallas contributed additional manufacturing capacity, which combined with Englewood's output to reach an impressive monthly total of approximately 574 P-51s in the year 1944. As the war progressed, production rates increased throughout that year, culminating in a peak of nearly 981 aircraft in January of 1945. Each P-51 Mustang was a complex assemblage, composed of roughly 15,000 individual parts, manufactured by hundreds of subcontractors across the United States. The engines, built by Packard in Detroit, were Merlin models produced at rates exceeding 300 units per month. The final assembly of a single P-51D required approximately 22,000 man-hours of labor, yet thanks to an efficient assembly line system, complete aircraft rolled off the production line at intervals of just a few hours. At maximum efficiency, a new Mustang could be completed approximately every 2 hours, an extraordinary feat of industrial organization and process management. The scale and efficiency of this American production system far surpassed anything Germany had managed to achieve, despite their own efforts. In early 1944, the Germans, operating under emergency priorities and using forced labor, managed to produce around 600 fighters per month through combined efforts of manufacturers like Messerschmitt and Focke-Wulf. This output, while significant, could not match the sheer scale of American manufacturing. Furthermore, the resource implications of German aircraft production were stark. American aluminum production in 1944 soared to roughly 1,250,000 tons per year, equivalent to about £2,500,000,000, marking a massive increase from the pre-war figure of approximately 164,000 tons in 1939. Germany's aluminum production, by comparison, peaked at roughly 250,000 tons annually and was steadily declining due to the strategic bombing of their factories and the loss of critical bauxite sources. The United States possessed approximately 10 times Germany's aluminum manufacturing capacity. Interestingly, the decision to produce drop tanks from paper rather than aluminum was not driven by a lack of metal. In fact, the U.S. had ample aluminum to produce every single drop tank in metal if it had been deemed necessary. Instead, paper was chosen because it was more economical and required less critical resource input, demonstrating how strategic manufacturing decisions could optimize resource use without compromising operational effectiveness. The development and deployment of specialized manufacturing equipment for Allied aircraft production revolutionized the German war effort in more ways than one. Not only did it streamline the production process, enabling faster assembly lines and higher output, but it also freed up valuable aluminum supplies, allowing this critical material to be redirected towards other essential military applications. Moreover, these advancements meant that aircraft could be produced more swiftly and with less reliance on highly skilled labor, which was in increasingly short supply as the war dragged on. This strategic shift was a calculated move rooted in careful optimization rather than desperation. The significance of these innovations resonated deeply within the Luftwaffe's technical and operational communities, where they became symbols of the shifting tide of the war. The drop tank, in particular, evolved into a potent emblem of American industrial resilience and resourcefulness, starkly illustrating the disparity in national capabilities between the two sides. Captured exemplars of these drop tanks were exhibited at technical briefings to Luftwaffe personnel, serving both as a showcase of enemy ingenuity and a stark reminder of the technological edge the Allies held. Pilots newly transitioning into fighter units were shown these tanks and engaged in exercises to calculate their implications for combat tactics. The underlying message was unmistakable. With extended range capabilities facilitated by such tanks, American fighters could now escort bombers deep into German territory, rendering prior defensive strategies obsolete. Previously, German fighters relied on waiting until Allied fighters exhausted their fuel supplies and turned back, effectively halting enemy bomber campaigns before reaching their targets. Now, however, German fighters would have to confront the Allied escorts directly, engaging in combat over Germany itself. These encounters were expected to be costly, both in terms of aircraft and experienced pilots, at a rate that Germany simply could not sustain over time. Throughout the spring of 1944, General Galland provided detailed operational assessments to the highest levels of Luftwaffe leadership, emphasizing the stark reality facing German fighters. He consistently underscored that the American P-51 Mustang was superior to German fighters when operating above 20,000 feet. Its speed surpassed that of the Bf-109 at high altitude, and it was more maneuverable than the FW-190, factors that made it a deadly adversary. With the additional fuel capacity provided by drop tanks, the Mustang could accompany bombers throughout their entire mission. Profile: from takeoff to return. German fighters, therefore, could no longer perform unopposed attacks on bomber formations once Allied escort fighters turned back to base. Every interception now involved fighting through a formidable fighter screen, increasing the risk and difficulty of these missions. As a result, Luftwaffe fighter losses began to climb steadily, reflecting a dire situation. In January of 1944, they lost approximately 90 fighters while claiming around 150 Allied aircraft destroyed. By the following month, February, losses had risen to roughly 160 German fighters against approximately 230 Allied aircraft, an unmistakable and troubling trend. The disparity was growing increasingly alarming, revealing that Germany's ability to replace its losses was falling behind the rate at which the Allies could replenish their own forces. The summer of 1944 marked a turning point, as the full impact of American escort fighter capabilities became painfully evident. The 8th Air Force launched deep penetration raids on a nearly daily basis, weather permitting, with Mustangs providing continuous escort from England across Germany and back. The mounting toll on German fighters was catastrophic. In June, German losses of single-engine fighters reached about 350 during operations defending the Reich, and the trend continued into July, with losses exceeding 350 fighters in the Western Theater alone, representing a monthly attrition rate of over 31%. August saw similar levels of attrition, with losses hovering around 36%. These relentless losses meant that experienced pilots, those who had accumulated hundreds of hours flying these aircraft, were being killed faster than new pilots could be trained and brought up to operational readiness. The pilots arriving from training schools usually had only around 50 to 150 hours of flight experience in their aircraft, in stark contrast to the 300 hours or more typical of seasoned American pilots. Many of these newly assigned German pilots had as little as 30 hours of flight time in the type before being thrust into combat. This critical experience gap, coupled with Germany's numerical inferiority and the constant presence of well-trained American P-51 escort fighters, made daylight operations over Germany increasingly perilous and unsustainable for the Luftwaffe. The combination of advanced American tactics, superior aircraft, and persistent air superiority posed an existential threat to German air defenses that Germany could scarcely counter, ultimately narrowing the Luftwaffe's options and exposing its vulnerabilities in a war of attrition it was rapidly losing. Throughout this period, R. Galan persistently submitted detailed reports and assessments to Hitler and the senior leadership of the Wehrmacht, providing a clear and unvarnished view of Germany's dire strategic situation. His report from September of 1944 laid out the reality with harsh honesty, emphasizing that the Luftwaffe was effectively incapable of winning the aerial conflict. The Germans faced insurmountable obstacles: their dwindling resources, the critical shortage of fuel, the declining numbers of operational aircraft, and the lack of adequately trained pilots all combined to handicap their efforts to challenge Allied air dominance. Meanwhile, the Americans demonstrated a remarkable ability to replace aircraft losses at a rate far faster than Germany could inflict them, creating an unbridgeable gap in air power. Germany's industrial capacity, once a formidable force, had become a limiting factor that no amount of combat operations could overcome. The only remaining strategy was to conserve every possible resource for the defense of vital targets, hoping that some form of political resolution or settlement might occur before the situation spiraled into complete collapse. Despite the relentless Allied bombing campaigns, the Germans continued to deploy paper drop tanks, which fell across German territory from late 1944 into the spring of 1945. A testament to their desperate attempts to extend the operational range of their fighters with the limited resources available. German civilians gradually learned to identify these distinctive cylindrical objects lying in fields and forests, initially confusing them with unexploded bombs, which often caused panic. It was only after military authorities clarified that these were harmless fuel tanks, empty, silver, and cylindrical, that the public's fears eased. Civil defense organizations provided instructions, reassuring the populace that these cylinders were simply discarded tanks from Allied aircraft, not explosive devices or weapons. The psychological impact of these falling tanks was significant and was reflected clearly in civilian morale reports. The sight of numerous enemy aircraft overhead, their contrails crisscrossing the sky as they casually released these empty fuel tanks, served as a stark visual reminder that the Allies possessed vast, wasteful resources, while Germany was desperately scavenging for every drop of fuel and every piece of aluminum to sustain its war effort. This disparity further demoralized the German people and reinforced the perception of inevitable collapse. Throughout 1944, technical intelligence efforts continued to analyze captured American equipment, but the focus increasingly shifted from understanding the capabilities of Allied technology to documenting the stark industrial disparities between the two nations. The question arose: could Germany produce similar paper drop tanks? From a technical standpoint, the answer was affirmative. German chemical industries could theoretically manufacture suitable resins, and their paper mills could produce kraft paper sufficient for such tanks. The manufacturing process was relatively simple, relying on basic chemical and paper production techniques. However, despite the technical feasibility, the practical reality was entirely different. Germany's chemical industry was already operating at maximum capacity, producing synthetic rubber, explosives, and other critical materials necessary for the war effort. Resin production for auxiliary items like the paper drop tanks could not be prioritized without compromising essential wartime needs. Similarly, the German paper industry was fully committed to fulfilling military requirements, producing maps, technical documents, and packaging materials. There was simply no operational necessity for extended-range drop tanks, and by late 1944, fuel shortages had grounded a significant portion of the Luftwaffe, severely limiting their operational range and flight capacity. Pilot training had been scaled back to minimal levels, and operational sorties were constrained primarily by fuel availability rather than aircraft availability. Developing and manufacturing drop tanks to extend fighter range made little sense under such circumstances, as there was barely enough fuel to sustain local defensive operations. The irony of the situation was sharp and bitter. While the Americans had devised an effective solution to their fighter range problem using paper fuel tanks, Germany found itself grounded by fuel shortages at the very same time, rendering any such innovations or efforts moot. The stark contrast was rooted in fundamental differences in industrial capacity, resource availability, and strategic priorities. The Americans had an abundance of everything: more raw materials, more manufacturing capacity, and more logistical resources, allowing them to experiment with and implement innovations like paper drop tanks effectively. Meanwhile, Germany's industrial base, strained and overextended, could not adapt or scale such innovations to meet their specific needs, ultimately contributing to their worsening strategic predicament. In the realm of aerial warfare, the technological and logistical demands for sustained combat were staggering. To keep their aircraft flying further and longer, the Allies needed not only more fuel but also an increased number of trained pilots, additional materials such as aluminum for construction, and a robust industrial infrastructure capable of mass production. Critical to this effort was the ability to produce sufficient excess capacity to develop solutions like paper drop tanks, lightweight, expendable fuel containers that could be dropped during missions to extend aircraft range without the need for strategic fuel reserves. Meanwhile, Germany found itself embroiled in a war of constrained resources, battling against an adversary for whom scarcity was a secondary concern. The Allies could simply produce more, fueled by their vast industrial capacity and relentless manpower. By the early months of 2045, the outcome of the conflict was no longer in serious doubt. The Soviet Red Army was advancing steadily towards the Uda River, a mere less than 50 miles from Berlin, signaling that the Soviet forces were on the brink of encircling the German capital. Meanwhile, the Western Allies, having recovered from the setbacks of the Ardennes offensive, pressed forward into the heart of Western Germany, nearing the Rhine River. The Luftwaffe, Germany's air force, could muster only sporadic resistance at this stage, its sorties limited not only by the dwindling availability of fuel but also by the heavy losses of experienced pilots, which further weakened its operational capabilities. Throughout this period, meticulous analysis of American military equipment continued at the Reikland facility, though by then, these studies had become largely academic exercises. The findings, meticulously documented for historical purposes, no longer held the power to alter the course of the ongoing conflict. The culmination of this analytical effort was a comprehensive report prepared in late January of 2045, focusing on the P-51 Mustang fighter and its drop tanks. This report examined every technical detail, from the Mustang's range capabilities and the construction methods of the drop tanks to production estimates and operational implications. Its conclusions were unequivocal. The P-51 Mustang, armed with disposable paper drop tanks made from non-strategic materials, had rendered the German homeland indefensible against American daylight bombing campaigns. Germany's industrial infrastructure was incapable of matching the scale of American fighter production. Its fuel supplies were insufficient to sustain continuous combat operations at the necessary levels, and its trained pilots were being lost faster than they could be replaced due to high attrition rates. The detailed report was archived within the Reich Air Ministry's records in late January, but whether the senior leadership actually read or comprehended its conclusions remains uncertain. By that point, the technical analyses confirming American capabilities were merely affirming what the battlefield had already demonstrated. The Luftwaffe, which had once dominated European skies in 1940, was now reduced to desperate, sporadic sorties, merely hoarding limited fuel supplies and launching attacks that could no longer influence the overall strategic situation. American fighters roamed freely over Germany, conducting attacks on targets of opportunity, escorting bombers on their missions, and establishing complete aerial supremacy across the skies. Each paper drop tank that fell from an American aircraft served as a stark reminder of the vast industrial disparity that had decisively favored the Allies in the air war. In June of 1944, a significant exhibition at Reikland displayed captured Allied aircraft to German Luftwaffe personnel, including multiple examples of the P-51 Mustang alongside B-17 and B-24 bombers, P-38 Lightnings, Lancaster bombers, Mosquito fighter bombers, Typhoon fighters, and various models of Spitfire. Thousands of Luftwaffe pilots and ground crew members toured the exhibit, inspecting enemy aircraft firsthand and gaining insight into the technological and industrial prowess of their adversaries. The display prominently featured the technical diagrams and explanations of the paper drop tanks, illustrating their construction and the strategic range advantages they conferred. The exhibition served a dual purpose, as an educational tool to understand the enemy's technological edge and as a stark, sobering reality check for German personnel. They could clearly see the high standards of Allied equipment, the standardization of components across different aircraft models, and the overwhelming capacity of Allied production, evidence of a war effort that had become a colossal industrial machine, capable of outproducing and out-technologizing Germany at every turn. The tangible understanding of aerial combat capabilities was often rooted in the concrete, physical examples of the equipment faced by pilots on a daily basis during the war. One such example was the Kampfgeschwader 200, a specialized Luftwaffe unit responsible for conducting covert operations, which included the rare and daring task of flying captured Allied aircraft. Throughout the year 1944, this unit operated several P-51 Mustangs, which served as invaluable test beds for assessing the performance of what many considered the most effective fighter of its time. These aircraft were primarily used for evaluation flights, where Luftwaffe test pilots could directly experience the aircraft's handling, visibility, and overall performance, gathering insights that would be critical for their understanding of enemy capabilities. Reports from pilots flying these P-51s consistently underscored the aircraft's exceptional visibility from the cockpit, especially in the later P-51D model equipped with a distinctive bubble canopy, which significantly improved pilots' situational awareness during combat. The Mustang earned praise for its remarkable stability in flight, its responsiveness to control inputs, and its outstanding performance at high altitudes. Its power plant, the Merlin engine, was noted for delivering smooth, reliable propulsion across the entire operational envelope, ensuring the aircraft could perform consistently under demanding conditions. Perhaps most notably, the P-51's range and endurance were truly extraordinary for a single-engine fighter. When fully fueled, including auxiliary drop tanks, the aircraft could stay airborne for more than 6 hours. This endurance enabled missions that would have been virtually impossible for German single-engine fighters, even when carrying external fuel tanks, thus giving the Allies a significant strategic advantage. The detailed technical insights gained at the Reichsluftfahrtministerium's research center in Rechlin, Germany, played a crucial role in shaping German defensive tactics during the final year of the war. Recognizing that Allied fighters, especially the P-51s, could reliably escort bombers across their entire missions, Luftwaffe fighter controllers attempted to concentrate their forces at specific points along flight routes. The goal was to achieve local air superiority by assembling German fighters into larger formations, thereby increasing their chances against the heavily guarded bomber streams. Achieving such concentration, however, was fraught with difficulties. Dispersed German units faced frequent logistical hurdles, including fuel shortages and communication problems, which hampered their ability to assemble quickly and effectively. Even when German fighters managed to position themselves advantageously, the presence of the P-51 escort fighters made attacking the bomber formations a highly costly endeavor. The tactical landscape had fundamentally shifted by mid-1944. Prior to this, unescorted or poorly protected bombers suffered devastating losses, but as the war progressed, the Germans found it increasingly difficult to mount effective offensive actions against the well-defended Allied airstreams. After the war, the small, lightweight paper drop tanks, used by the P-51s to extend their range, became rare collector's items. Few of these tanks have survived intact to modern times, as most were either destroyed upon impact or deliberately crushed by Allied ground crews to prevent their reuse by enemy forces. Their disposable nature meant that they held little intrinsic value at the time, making surviving examples even more precious. Today, those that do remain are displayed in museums as historical artifacts, offering tangible links to the technological and tactical realities of wartime aviation. One prominent example is the National Air and Space Museum in Washington, D.C., which maintains several of these drop tanks in its extensive collection. These tanks are displayed alongside P-51 Mustangs, illustrating their purpose and significance. Informational placards detail their construction, laminated craft paper impregnated with phenolic resin, and note that their manufacturing was carried out by companies such as Bowater Scott. They also specify their capacity as approximately 108 U.S. gallons, emphasizing their role in extending the operational range of the aircraft. Interestingly, the placards often omit a crucial aspect of the tank's significance. German engineers spent weeks analyzing these seemingly simple devices. Their detailed studies involved analyzing the tank's construction materials, manufacturing techniques, and performance implications. Through this meticulous examination, they gained a comprehensive understanding of the full scope of Allied industrial and logistical superiority, gleaning insights into the scale and sophistication of the Allied war effort. This knowledge not only informed German tactical responses but also highlighted the ingenuity and adaptability of Allied technological innovation during the conflict. The Second World War continued to demonstrate their value in subsequent conflicts, cementing the aircraft's reputation as a versatile and reliable platform. The aircraft's ability to perform effectively over extended periods, combined with its impressive maneuverability and firepower, allowed it to adapt seamlessly to different combat environments, including the tense skies of the Korean Peninsula. During this conflict, the P-51 Mustang was predominantly employed in roles such as ground attack and close air support, where its long-range capabilities and durability proved invaluable. Its operational endurance enabled pilots to carry out sustained missions deep into enemy territory, often providing vital assistance to ground forces engaged in intense battles. The importance of the Mustang's extended operational range was a direct continuation of the strategic advantages it had demonstrated during World War II. Its endurance allowed for longer sorties without the need for frequent refueling, which not only increased mission effectiveness but also reduced the logistical burden on Allied air forces. This characteristic became especially crucial in the rugged and often unpredictable terrain of Korea, where supply and support lines were frequently stretched thin. The aircraft's adaptability in different combat scenarios highlighted the foresight of the design principles that prioritized standardization and ease of production, which had been emphasized by the German engineers' post-war studies and the lessons they carried into their future work. Furthermore, the legacy of the P-51 Mustang extended beyond its combat service. Its design and manufacturing principles influenced post-war aviation development worldwide. Engineers who had studied captured aircraft and internal German documentation, many of whom later migrated to the United States, brought with them invaluable insights into American manufacturing philosophies. These included a focus on standardization, the interchangeability of parts, and designing aircraft for mass production, principles that became the cornerstone of modern aerospace engineering. The innovative use of the paper drop tank exemplified wartime industrial ingenuity and resourcefulness. It was often showcased in engineering curricula and military training programs as a prime example of how optimizing resource use and leveraging mass production capabilities could confer strategic advantages. The success of such innovations underscored the impact of industrial capacity on wartime outcomes, demonstrating that technological sophistication was not the sole determinant of victory. Efficient production and resource management played a crucial role as well. The enduring legacy of the P-51 Mustang and similar aircraft is reflected in their continued use in various air forces well into the post-war years. Their deployment in conflicts like the Korean War underscored their versatility and effectiveness in multiple combat roles beyond their original escort mission. The aircraft's proven endurance, combined with the lessons learned from wartime innovations, helped shape the development of subsequent generations of military aircraft. In essence, the story of the paper drop tank and the P-51 Mustang encapsulates a broader narrative about wartime innovation, resourcefulness, and strategic thinking. It highlights how technological simplicity, when combined with industrial efficiency, can deliver a decisive edge in warfare. Moreover, the insights gained from these innovations had a lasting impact on the post-war development of aviation technology, influencing the design philosophies and manufacturing practices of future aircraft. The legacy of these innovations continues to serve as a testament to the power of resourcefulness and strategic planning in achieving military and technological success over the course of history. Europe, with its diverse military landscape, proved to be as significant a testing ground for the P-51 Mustang as any other theater of war. Despite operating in vastly different conditions and environments, the aircraft consistently demonstrated its versatility and reliability. Remarkably, some P-51s remained in active frontline service with various air forces well into the early 1980s, a testament to the robustness of its fundamental design and engineering. This durability, combined with its exceptional performance, underscored the aircraft's importance during and after the conflict. In total, more than 15,000 Mustangs were produced during the course of the war and in the immediate aftermath, making it one of the most prolific fighters ever designed by the United States. This massive production volume not only highlights the aircraft's popularity but also reflects the rapid industrial mobilization that characterized America's wartime effort. Today, there are still over 100 P-51s that are airworthy around the world, meticulously maintained by dedicated collectors and museums. When glimpsing a Mustang soaring through the sky, often still bearing the distinctive markings of the units from the war period, one is reminded of the aircraft's pivotal role in achieving and maintaining Allied air superiority over Europe. The significance of the P-51 Mustang and its auxiliary equipment, such as the iconic paper drop tanks, extends far beyond their immediate tactical use. These elements serve as powerful symbols of the broader industrial achievements during World War II. They exemplify how modern warfare was fundamentally shaped by a nation's capacity to produce vast quantities of military hardware and supplies. The outcome of the war was, in many ways, decided not solely on the battlefield but in factories and factories alone. The ability to produce more weapons, ammunition, aircraft, ships, and vital supplies at a faster rate than they were consumed in combat provided a decisive advantage. The United States, in particular, achieved an unparalleled level of industrial mobilization. During the peak years of 1943 and 1944, American factories operated at extraordinary scales, producing over 50,000 aircraft annually, launching multiple ships every single day, and manufacturing ammunition in quantities measured in billions of rounds. Such output supported not only American forces but also significantly supplied Britain, the Soviet Union, and other Allied nations through the Lend-Lease program. Germany, despite possessing a substantial industrial base and advanced technical expertise, could not match the Allies' industrial output. Their challenges stemmed from several factors: a smaller industrial base, strategic bombing campaigns targeting their production facilities, loss of access to raw materials as territories fell to the Allies, and the diversion of resources to various competing priorities. Moreover, inefficiencies in organization and planning further hampered their efforts. Fundamentally, though, the core issue was that Germany was fighting a coalition whose combined industrial capacity vastly exceeded its own, making victory increasingly implausible. The addition of American industrial strength to the Allied cause, particularly from 1942 through 1943, made the Axis powers' defeat inevitable once their full mobilization was reached. The paper drop tanks, which rained down across Germany in the years from 1944 to 1945, became stark symbols of this industrial disparity. Their simple, unassuming form conveyed an unmistakable message: the overwhelming industrial might of the Allies had tipped the scales decisively. Throughout the war, German technical intelligence units systematically and professionally examined captured American equipment. Facilities like Reikland maintained detailed records of performance tests, material analyses, and technical evaluations. Many of these documents survived the conflict and are now preserved in various archives, offering valuable insights into how each side perceived the technological capabilities of their adversaries. These assessments, particularly those made by German experts, were generally accurate in technical terms, accurately identifying the strengths and weaknesses of American equipment and tactics. The strengths and weaknesses of American aircraft, vehicles, and weapons during World War II reveal a complex interplay of technological innovation and industrial capacity. While the American military technology was often superb, it was the extraordinary scale of American industrial production that truly set them apart from their adversaries. The critical flaw in German analysis was not in understanding the capabilities of individual equipment, such as fighters, bombers, or tanks, but in failing to grasp the sheer magnitude of American manufacturing power. This massive output had profound implications for the eventual outcome of the war. Take, for instance, the iconic P-51 Mustang fighter aircraft, an aircraft widely regarded as one of the finest fighters of the conflict. When considering the enormous fleet of American fighters, numbering in the tens of thousands, it's clear that air superiority was virtually assured. Such a formidable force, representing a level of production that no tactical ingenuity or technical innovation could fully counteract, provided the Allies with unprecedented dominance in the skies. The story of German engineers examining the paper drop tanks at Recklen in March of the year 1944 exemplifies this point vividly. Their analysis was not just about the tanks themselves but about what they symbolized, the nature of industrial warfare itself. This episode underscores a vital lesson, learned during the war, that in conflicts between highly industrialized nations, the ability to produce vast quantities of war material becomes as crucial as battlefield tactics. The nation that can manufacture more, faster, and more efficiently holds a decisive advantage, often tipping the balance even when faced with equally skilled opponents. Tactical skill and technological innovation, while important, cannot completely offset the advantages conferred by superior production capacity. This lesson, painfully learned through the costly experiences of Germany and Japan, shaped military planning during the Cold War era and continues to influence strategic thinking in the modern era. The capacity to sustain continuous production of advanced weaponry, to maintain efficient supply chains under intense stress, and to train personnel at a pace that surpasses losses in combat. These factors remain just as vital today as they were in 1944. The ability to outproduce an adversary over extended periods can determine the outcome of a protracted conflict, underscoring the importance of industrial resilience and logistical efficiency. The pivotal moment in the air war over Europe occurred in March of the year 1944, when the first long-range, all-escort bombing missions to Berlin took place. These missions were significant because they marked a decisive turning point. For the first time, American bombers could reach deep into Germany's heartland under the protective cover of escort fighters. No longer were targets in Germany beyond the reach of effective American aerial assault. The systematic bombing campaign, now supported by robust fighter escort, could proceed with losses, though still substantial, that remained sustainable over time. This shift placed increasing pressure on German war production, which was a central aim of Allied strategic bombing. Factories producing synthetic fuel, ball bearings essential for machinery and vehicles, aircraft manufacturing plants, and vital transportation infrastructure all became regular targets. The presence of fighter escorts throughout these missions meant that the Allies could strike repeatedly with relative safety, gradually eroding Germany's industrial capacity. The combined pressure from the air campaign, Allied ground advances from the west, and Soviet pushes from the east culminated in Germany's defeat. A victory achieved just 14 months after the first P-51 Mustangs arrived in Berlin. Throughout this final phase of the war, paper drop tanks proved indispensable. Their production continued robustly into 1945, with thousands manufactured each month, extending the operational range of American fighters significantly. These tanks were not only used by the P-51 Mustangs but also by other American fighters such as the P-47 Thunderbolt and the P-38 Lightning, effectively broadening the reach of all combat aircraft in the Allied arsenal. British fighters, too, adopted the use of paper drop tanks extensively, particularly during long-range missions over occupied Europe and into Germany. The strategic advantage gained from the paper tanks was twofold. Firstly, their efficient production freed up aluminum and steel, materials critical for manufacturing other vital war equipment, thereby optimizing resource allocation. Secondly, they enabled fighters to undertake longer-range missions, which was essential for the strategic bombing campaigns and interdiction efforts. This approach exemplified the industrial mindset that permeated Allied military operations, prioritizing efficiency, resourcefulness, and innovation over traditional methods. It reflected a broader trend throughout the war: the integration of industrial engineering principles into military strategy. Today, historians studying the air war over Europe recognize multiple factors that contributed to Allied victory, among which the unparalleled industrial capacity and logistical innovation stand paramount. The ability to produce vast quantities of aircraft, weapons, and supporting equipment at an unprecedented scale proved decisive. The lessons derived from this period continue to resonate, shaping modern strategic thought and emphasizing the importance of industrial strength in achieving military victory. From a combination of factors that went far beyond the simple addition of paper-drop tanks, these aircraft played a crucial role in the broader context of the Allied victory, which was achieved through a complex interplay of technological innovation, industrial capacity, strategic planning, and relentless operational effort. The Allies' numerical superiority in both aircraft and trained pilots was a decisive advantage, enabling sustained dominance in the skies over Europe and beyond. In parallel, technological advancements, such as the development and deployment of sophisticated radar systems and improved communication networks, greatly enhanced command and control capabilities, allowing for more effective coordination of large-scale air operations. The strategic bombing campaigns directed at German industrial centers and transportation infrastructure further weakened the Axis war effort by crippling production and logistics, thereby accelerating the depletion of German resources at a pace that their military industry could not compensate for through repairs and new manufacturing. Within this multifaceted campaign, the P-51 Mustang and its innovative use of paper-drop tanks epitomized the ingenuity employed to extend the operational reach of Allied fighters. These auxiliary fuel tanks, made from lightweight paper and designed for single use, became a symbolic element of the larger industrial effort that underpinned Allied success. However, it is important to recognize that the aircraft's victory was not solely due to these tanks. Rather, it was the result of a synchronized combination of varied fighter types, strategic bombing, continuous pilot training, technological innovation, and the steady commitment of vast resources. The paper-drop tank stands out as a noteworthy symbol because it visually and practically embodied the industrial and logistical advantages that the Allies harnessed during the war. The detailed technical documentation preserved in records maintained by institutions such as the Royal Canadian Institute, RCIN, provides a clear window into American industrial capabilities. These files meticulously recorded specifications, performance data, manufacturing techniques, and production estimates, reflecting the thoroughness characteristic of German engineering documentation of the era. Such archives, including those housed in Germany's Federal Archives, offer modern historians a detailed, contemporary perspective on the technical assessments of Allied equipment, as viewed from the German side. When these documents are examined today, benefiting from the perspective of historical hindsight and access to American records, it becomes evident that German engineers correctly understood the capabilities and limitations of the American aircraft and auxiliary systems. What they couldn't influence, however, was the strategic reality that these capabilities represented. Recognizing an opponent's overwhelming technological and industrial advantage does not enable the adversary to counteract it directly, especially when such advantages are rooted in fundamental disparities of industrial capacity and resource availability. Ultimately, the German technical analyses, while accurate, could not alter the strategic imbalance created by Allied industrial and logistical superiority. The legacy of the paper drop tank extends beyond its operational utility during the war. it serves as a lasting reminder that effective solutions do not need to be overly complex or technologically elaborate. A simple, functional design, crafted from inexpensive, readily available materials, proved sufficient for its purpose of extending fighter aircraft range. The concept of designing a solution that is good enough for the task at hand, rather than striving for technological perfection, emerged as a core principle in modern systems engineering. This approach emphasizes that the optimal answer to a problem is often the one that can be produced efficiently, affordably, and within the necessary timeframe, using accessible resources. The success of the paper drop tank in crossing Germany's skies remains a valuable lesson in practicality and resourcefulness, applicable not only to military technology but also to civilian engineering challenges today. The aircraft that carried these innovative tanks, the P-51 Mustang, stands as one of the most successful and iconic fighter designs in the history of aviation. Its combination of long-range capability, high performance, operational reliability, and ease of manufacturing made it an exceptional escort fighter during the strategic bombing campaigns over Europe. The Mustang's effectiveness was a direct result of this harmonious blend of design and operational versatility, which contributed significantly to the Allied victory, ultimately demonstrating that sometimes, simplicity paired with ingenuity can be the most powerful solution of all. The remarkable success of the P-51 Mustang in the European theater of World War II was not the product of a single innovative feature, but rather the result of a complex and carefully coordinated integration of multiple technological and strategic factors. Central to its effectiveness was the aerodynamically refined airframe, expertly engineered by the talented team at North American Aviation under the leadership of Edgar Schmood. Complementing this was the formidable and dependable Merlin engine, whose power and reliability significantly enhanced the aircraft's performance. To further extend its operational range, designers incorporated a fuselage fuel tank that substantially increased the Mustang's endurance, and the availability of auxiliary drop tanks. Small, easily detachable fuel containers pushed its operational radius well beyond 800 miles. However, it is crucial to recognize that no single element alone was sufficient to make the Mustang a decisive weapon. Instead, it was the seamless integration of all these components, supported by the robust industrial capacity capable of mass production, that established the P-51 as the quintessential escort fighter of the European air war. This synergy of engineering excellence, resource availability, and manufacturing efficiency turned the Mustang into a symbol of technological achievement and strategic dominance. Looking back over the span of 80 years since the events of March in the year 1944, the lessons derived from these developments remain profoundly instructive. They serve as a reminder of how technological innovation, strategic planning, and industrial strength intertwine to influence the outcome of conflicts. In a revealing episode, German engineers at Rechlin captured and examined equipment from the conflict, uncovering not just the technical specifications but also the broader strategic realities faced by the Allies. The discovery of paper drop tanks, crafted from glued paper and designed to hold fuel, provided critical insights. These tanks demonstrated that the United States possessed an industrial capacity far exceeding that of Germany, capable of producing innovative solutions at an extraordinary scale. The examination also highlighted that American engineering prioritized practicality and functionality over the pursuit of technical perfection, a mindset that proved pivotal in wartime production. Furthermore, these findings revealed that the Allies had sufficient resources to optimize their operations without resorting to desperate or makeshift solutions. The significance of these revelations came at a time, March of 1944, when the outcome of the war was still uncertain, but the overall trajectory was becoming increasingly clear. German technical personnel gained a stark understanding of the formidable challenges confronting them. Yet, this knowledge, however insightful, could not alter the fundamental course of events. Germany's defeat was predestined by larger strategic and industrial forces beyond the reach of individual engineers or testing facilities. Nevertheless, the story of those engineers, painstakingly analyzing paper cylinders of glued kraft paper, calculating fuel capacities, and comprehending their implications for aerial combat, provides valuable insight into how industrial capacity and technological ingenuity shape modern warfare. The outcome of the conflict was ultimately decided not solely on the battlefield but also through the effective mobilization of industrial resources and technological innovation. By May of 1945, the war in Europe drew to a close. The relentless, systematic bombing campaigns, bolstered by the long-range fighter escorts like the P-51 Mustang, equipped with auxiliary drop tanks, had played a crucial role in crippling Germany's war-making ability. The destruction of industrial facilities, the devastation of transportation networks, and the depletion of fuel supplies all contributed to the collapse of the German war effort. The Luftwaffe was reduced to a mere shadow of its former self, operating as a token force rather than an effective combatant. These outcomes resulted from a confluence of factors stretching over several years, but the capacity of fighters such as the P-51 Mustang, enabled by the innovative use of drop tanks, including those made from paper, was among the decisive elements. The paper drop tanks themselves, some of which survive as historical artifacts in museums today, symbolize a broader story of technological ingenuity and strategic purpose. Most of these tanks, however, were destroyed or discarded after the war. Their true significance transcends the physical object. It lies in what they represented: the extraordinary industrial capacity applied with precision and strategic intent, the deployment of technology tailored to meet specific wartime needs, and the overwhelming advantage gained through mass production. The story of these tanks, preserved in technical reports from Rechlin and other archives, continues to deepen our understanding of World War II and illustrates the fundamental role industrial strength and technological innovation play in modern conflict.